Okay, welcome to the second session in the morning today. It's a pleasure for me that I can chair this, and I just have to keep a look at the time of the people talking. The first talk will be given by Elina on the atomic precision measurements for the high-frequency gravitational waves. I hand over the talk, and actually Elina has some great news she wants to share for sure.
Hi. First of all, thanks a lot for organizing this exciting workshop and for including me. I'm Elina. I'm from the Leibniz University of Hannover, and PTB stands for Physikalisch-Technische Bundesanstalt, which means it's the National Metrology Institute of Germany. It has two sites in Braunschweig and in Berlin. I'm part of the Braunschweig place, where amazing atomic clocks are being built, and there's a whole hall of atomic clocks. And the announcement is that I will soon switch to DESY, and I will keep the Leibniz University, but I still hope to collaborate also with the atomic clock people in Braunschweig. So I will speak about our joint work together with two of the organizers, Valerie Dunke and Joachim Kopp, and also with Thorsten Brinkmann, who was here at CERN for a while and who unfortunately cannot be here at this workshop today. It was a project it was a roller coaster about finding possibilities to detect high-frequency gravitational waves with atomic precision measurements. So in my talk, I will tell you about some theoretical insights on from our journey to this topic, and on some possibilities of which we think that will work, that can be put into practice, and also a few side steps from the roller coaster of insights where we thought this won't work. And why? So let me start. So we have heard already about some types of quantum sensors in this conference. And so I wanted to say just a few words about what we understand under quantum sensors, and then I will switch directly to atomic clocks as the quantum sensors of choice for the following. So quantum sensors need that we have discrete resolvable energy levels. We can model them as a two-level system, and they are separated by some discrete energy. We should be able to initialize the quantum system in a known state and read it out such that we can detect if a change of the state has happened. The quantum system we should be able to coherently manipulate it. And there should be an interaction with an external field that will change the energy gap between these levels. So under this buzzword quantum sensors, there are different realizations how you can build a quantum sensor based on atoms or ions in some lower-lying states or in some highly excited Rydberg states. Complementary systems are superconducting circuits, cavities, in general atomic clocks, and interferometers. So these are systems that just use these properties, but on top you can use inherent quantum properties like entanglement or a squeezing of states that was also used in some of the talks before, to enhance your capabilities to reduce, in particular, noise. So such quantum sensors in general are well suited for detection of new physics and gravitational waves. Typically, they are used at low energies, but they can also be employed at high energy detectors, some of them. So here to move to atomic clocks, I will use a citation by a Nobel laureate, Arthur Shavlov, who said, "Never measure anything but frequency, because this is the thing that you can measure most precisely. So how can we use very precise frequency measurements as an opportunity for gravitational wave searches?" But first of all, what is an atomic clock? So we go back to this definition of a two-level system separated by some discrete energy. Here we model it by some ground state and excited state. Then we can shine a laser onto this system and tune the laser such that the frequency will hit exactly the resonance, will hit the energy gap. And then we lock the laser. And we want to find the peak frequency and the width of this transition. To translate also optical clock measurements at high frequency, optical combs are used to translate this into a counter. So then, like the Z boson line shape was measured, was scanned, one can scan a resonance of an atomic transition. So you count if you shine a laser with a frequency somewhere here, you excite the system less often, and the more you approach the peak, you will see more transitions, and when you move away from the peak, it will decrease, so you can determine your peak frequency and the width. So this has led to an impressive precision in the atomic clock community, starting with microwave clocks and switching to optical clocks, that mean with frequencies in the optical range. And when the optical clocks started, they were still more than an order of magnitude worse than the microwave clocks at that time, but people didn't give up, and the slope was very steep, so nowadays the optical clocks give the highest sensitivity, reaching in many systems already a relative precision. That means the frequency uncertainty over the frequency of 10 to minus 18, and recently even measurements at 10 to minus 20 have been achieved in optical lattice clocks, comparing two different atomic samples. So it's the key to such precision are often differential measurements where common uncertainties cancel. Okay, so if we see such precisions, can we ask, in our context of this workshop, can we ask, can we translate relative frequency precision of 10 to the minus 20 to a gravitational strain of 10 to the minus 20? That would be the hope. Let's see, we will come back to that. Let's see where the limitations are and what are the possibilities. So first of all, we will define the setup. Our goal is to study the photon in a gravitational field and to calculate the change of the photon frequency measured at a source and at a detector in different frames. So we assume here a photon propagation along one axis, let's say x1, of a length L between a source and a detector. And it has some initial photon momentum defined at the time of the emission in the system of the sender of the source. The resolution. Oops, sorry for this resolution. And what we study then is the propagation of a gravitational wave. Here in this context, of course, a high-frequency gravitational wave, but still lower frequency than the optical photon. Okay, so the gravitational wave perturbs the metric, and we see here the effect on the metric and on the momentum. And we will, in the following, always keep terms up to order h in the gravitational wave strain. And then via the geodesic equation, we arrive at the master formula describing the frequency change measured between the detector and the source, normalized by the frequency at the detector, expressed in terms of the tensor elements h. So this is still in a quite abstract way, but we can see the physical sources. This first line describes the effect of the variation of the varying gravitational field along the photon trajectory. And the second term, you see it's specific for the detector and the sender, so this is due to the motion of the source and the detector. Okay, so this is still without reference to a frame. And now we will study two different cases. On the one hand, free-falling detectors and then rigid setups. And for the free-falling detectors, we compare between the two different frames, the transverse traceless frame and the next frame, so proper detector frame. Oh, sorry, I clicked in the wrong direction. So we imagine the system where the source and the detector are in free fall, or at least the minimal requirement we have to do is that they move freely in the direction of the photon propagation. To simplify the expression, it's most convenient to work in the transverse traceless gauge, where some elements of h vanish. And then we express the element h11 in the transverse traceless gauge, and it depends on the h plus because the transverse polarization does not have an effect here. And the expression we had on the previous slide was exactly this, the relative difference between the photon frequency at the detector and the source. And here it's conveniently expressed in terms of the physical quantities Here we see the angle theta of the gravitational wave relative to the x-axis and the initial phase phi naught and the h plus. So we will always keep track of the dependence on h plus. Okay, so this is one result. Then if we want to check the frame independence, we consider the same physical situation, still free falling detectors, but this time in this, I always forget the name, proper detector frame. So, no, same mistake. So here, the expressions, the two terms add up from the photon propagation and of the Doppler shift. And we see, and we have to be careful when we want to compare the two results, we have to be careful with the initial conditions. So to make them comparable, we go into a setup where we gradually switch on the gravitational wave. And then we see that in these two terms, there are these blue boxes which appear with an opposite sign. So these are terms that are proportional to the gravitational wave frequency omega gamma times the length of the propagation L. But they appear with opposite signs, so they cancel out. So such a term could give an interesting enhancement of omega gamma times L, but they cancel out. And then taking the sum of both terms recovers the result of the free-falling detector in the TT frame. Then we can move to the next system. So if we now leave the free-falling system aside and we go into a rigid setup, here we choose the proper detector frame to express this relative difference of the photon frequency at the detector compared to the source. And we see terms, again, proportional to H plus. And we see terms growing with a product of omega g times L or even squared. So that could give some hope to say, oh, if this product is large, maybe we will observe a large shift. Can we make it arbitrarily large? But then we have to keep in mind that no material is perfectly rigid at high frequencies. So if we calculate in a rigid setup, we have to make sure that this assumption is valid. And unfortunately, I missed the talks on Monday, but I saw that Sebastian compared the systems of long wavelengths to the length of to the length L of a ruler of a rigid bar, which is rigid if for long wavelengths, and which is no longer rigid for short wavelengths. So this is a nice illustration of this case. So we have to keep in mind that for large products of omega of the gravitational wave times the length of the propagation, when it's larger than the sound velocity, we cannot assume a perfectly rigid setup anymore. So this question doesn't make sense to ask if we can go to arbitrarily high limit of omega g times L. So this was not intuitive for us from the start, so we thought, we learned something on the way, on the theoretical side. Okay, so this was the theoretical part. Now we switch to the detection possibilities. So our goal is to make to make this effect detectable by a clever choice of a detector. How can we detect subtle effects of this frequency change? Against our naive expectation that the gravitational wave would directly change the photon frequency and we can perform a precision atomic clock measurement, we learned that the effect we have to expect are the creation of sidebands. And interestingly, the sidebands are separated from the carrier line, so the original photon frequency, by the gravitational wave frequency. So if we want to have a large separation, it's favorable to look at high frequency gravitational waves. So it's a good context for this workshop. Still, if we look at order terahertz photon frequencies and a gigahertz gravitational wave, it's still a small shift. We cannot say it's a high frequency means high enough shift. Then the sideband amplitude goes with h, so the intensity goes with h squared. And if we target unexcluded gravitational wave strains of h of order 10 to minus 20, we are hit by a suppression of 10 to minus 40. So the straightforward way is less promising, so we have to find a way of how to make such a feeble effect detectable. And what we have to keep in mind is even if we have a gigahertz separation between the carrier line and the sideband, the carrier is not sharp, it's not a delta function. It has a width, a natural width, and also a resolution. So we have to know, or at least estimate, how much of the carrier line will spill into the sideband. So what is the tail at the separation of 1 gigahertz or order gigahertz? For this, we looked at different possibilities. So what can we do if we design a filter that blocks out this overwhelming carrier line? How much will be left outside of this filter area that we define somehow, that we have to find a filter system that blocks out this line? That would be the hope to have some direct detection of sidebands. And that would mean that one has to detect a few photons above the background that remain here. And of course, this figure is not to scale. While the interference term would only be suppressed by order h instead of h squared, it's already cut out before it can interfere. So this route does not help. So we looked at systems to get a feeling about what kind of filter can be built. And for this, 2 parameters are essential. One is the bandwidth that we filter out and the suppression of the carrier. And we parameterize them by these delta lambda and alpha t. Later in the limit plots, you will see these parameters as assumptions that go into the numerical limits. So I mentioned I work at PTB, so I asked colleagues who are familiar with the capabilities of the cavities at PTB. And a recent one reaches a finesse of 500,000 at a length of 30 centimeters and reaches a bandwidth of order kilohertz. That is like one order of magnitude one can look at. Another possibility we discussed are fiber Bragg gratings that cut out of an incident spectrum of frequencies, cut out some range of frequencies and leave out a transmitted spectrum. And there's already some industrial fabrication of fiber Bragg cavities, but it's a bit difficult to find out which ones are really sufficient for the scientific purpose of reaching the highest precisions. So we looked at an additional possibility, namely using atomic clocks, where you can see here an example of frequencies where the parameters are chosen for illustration purposes. You can see in arbitrary units of time the photon amplitude shown in orange. What happens if the photon propagates without the gravitational wave signal, and how it propagates in the presence of a gravitational wave. That is modeled here by this green line. So we see within one period of going from one peak to another, the phase modulation is averaged out during the gravitational wave period. So a phase modulation is achieved, but after one period of propagation, we cannot observe it anymore. So the only thing one observes in this case is the peak frequency, carrier line, and the sideband separated by the gravitational wave frequency omega g. But we don't see a frequency shift of the photon. So the idea is to build an optical rectifier to stop the photon propagation during a part of the gravitational wave period. And that, so if we block the propagation at some time, this phase modulation will not average out, but some net frequency shift will remain. And that could be detected. So the effect will be this. The photon propagation will be blocked. Again, in orange, you see the unperturbed photon propagation. And you see on the right-hand side an effect with and without the shutter, which is just an effect of the shutter. It's not an effect of the frequency. If we look at the orange line where no gravitational wave was propagating. But if we now observe the comparison of the orange line of the photon propagating without the presence of the gravitational wave compared to the purple line where the photon propagation is alternated by the gravitational wave, you see a net modulation remaining that can cause, in these over-exaggerated parameters for illustration purposes, a net frequency shift, in addition to the sidebands. Okay. For this, we can consider different limits at small product of the the gravitational frequency times the propagation length L, and similarly at the large product. And this brings me to the discussion of the limits that we estimate with these methods. So we see here the gravitational wave frequency in gigahertz and the gravitational wave amplitude h. And to put some numerical limits, one has to plug in certain assumptions on the setup. So this is what we used. Crucial for these approaches is to know the integration time. So here it's set to 1 second, and it's for a fixed length. We choose an original photon frequency at the source in the optical range. And at the end, we need a high enough number of photons, so we have to choose a powerful enough laser originally. And here we compare different limits. First of all, we are not in the vacuum. There are many limits achieved by people in this audience that we see in this plot also, like interferometers and the MAGO cavities and the dark matter radio, levitated sensors that we heard about, bulk acoustic wave devices, and the holometer experiment. So these are the experiments already on the market or with projected limits of their capabilities. So how do these atomic methods compare? On the one hand, the detection of sidebands has the potential to cover a quite broad range of frequencies, and this is common to the methods that we propose here. However, the sensitivity in terms of H is limited. And the atomic, so for the sidebands, we had to plug in certain assumptions on the transmission and also on the thermal noise. So you see the 3 different versions of the limits of a conservative estimate, how much the filter can work, what we call realistic or optimistic scenarios. Also for the other experimental estimates. Our conclusion is that the method based on atomic clocks with an optical rectifier has the best sensitivity among our proposals, but also there the exact sensitivity depends on the assumptions that we plug in. And again, it can span many orders of magnitude in the frequency. The previous plot was for 1 second of an integration time. If we switch to 10 to the 5 seconds, we see that the limits shift a bit. So you see here the best ones were at the order of 10 to minus 22 for the bulk acoustic wave devices. And here we switch to 10 to minus 24. But the relative ordering of the bounds remains similar. So the comparison of the limits, the conclusion is relatively unchanged, but we see a strong sensitivity to the integration time. Okay, so I want to come back to the initial question is, if we achieve relative precision of frequency measurements of down to 10 to minus 18 or even 10 to minus 20, why can we not directly test gravitational wave strains of 10 to minus 20? Here, this is the picture of the publication that achieved these 10 to minus 20 and managed to test sub-millimeter scale gravitational redshift within 2 samples of an atomic clock, so already a remarkable application. But why doesn't it apply directly to the gravitational wave case? So typically, these record precisions in the atomic clocks require long integration times, and that means that depending on the signal, the signal cannot be resolved anymore. Another argument is when we look at the sizes. A typical atomic size is an angstrom, but that's much smaller than the wavelengths of a gigahertz or 100 gigahertz gravitational wave. So the gravitational wave signal gets suppressed. So we could think we could use bigger systems to overcome this suppression of scales. So what if we don't look at atoms or ions close to their ground state, where the valence electron is relatively close to the nucleus, but what if we excite them to highly excited states, so-called Rydberg states, where the electron is far away from the nucleus, even at orders of micrometers. But this is still insufficient. In particular, we have to compete with a strong Coulomb interaction. So what if we go to even larger systems? So if we imagine an atom as a small cyclotron, what if we have a look at a really big cyclotron on these scales? We could look at the muon G minus 2, which is one of the most precisely measured quantities. Could this be sensitive to the perturbation of a gravitational wave? So if we compare the precession frequency with the cyclotron frequency, one can determine their difference at a precision of roughly 10 to minus 6. And we expect the leading effect of the gravitational wave to be visible in the cyclotron frequency, which would go in leading order with h, and one would be able to test strains of 10 to the minus 8. Which is highly non-competitive. So even if there's no obvious showstopper from the start, if you plug in the numbers, at least what we found is that the numbers are not sufficient to probe gravitational waves in an untested territory. Okay, this brings me to my conclusion. We discussed high-frequency gravitational wave detection via different methods of optical frequency modulation. On the way, we learned about fundamental limitations and see that a perfectly rigid detector is not possible at high omega of the gravitational wave times the propagation length. We investigated different proposals, out of which the atomic clocks with an optical rectifier, where we block the photon propagation, look most promising to us. In conclusion, we see that it's challenging but not impossible and promising to test gravitational waves over a broad frequency range. And I invite you to also look at our appendix, of which I discussed these 2 examples that didn't work. We listed a few more examples that didn't work, but maybe they can avoid others. They can avoid that others will spend time on them, or maybe you will find some workarounds about where we stopped. Thank you very much.
Yeah, many thanks, Elina. I would allow 1 or 2 questions for a brief, just for understanding, yeah? Not comments. So, yes, Axel, maybe you go first.
Thank you very much. So on slide 31 or so, you had the sideband with some parameters. Mm-hmm. Yeah. How does this alpha thermal, for example, 10 to the minus 19, translate to temperatures or so? What's behind this?
I have to look up the exact conversion. Yeah, but for experimentalists, this will be the relevant number. So it was just to count the photons above the noise and to model also the thermal noise. Maybe Joachim or Valerie, you know these numbers.
Yes.
Sorry, short question. Not only is integration time relevant, but also sampling time. Mm-hmm. So what are your sampling times? Could you go down to nanoseconds?
So which properties do you mean? What should be measured in nanosecond?
Distinguish whether the signal is lasting for less than a nanosecond or not. Is it very sharp? Time?
Yeah, well, this depends a bit on the method.
I think maybe
Valerie wants to, yeah.
Yeah, so I mean, I don't think that's a concern here, because we're not trying to resolve the waveform, right? So we're integrating.
So just power.
It's just power, yeah.
Then there was, okay, let's just there, then Joachim.
So about the question of the alpha thermal, so the 10 to the minus 17, that's a level that has been achieved in optical fibers. That's why we call it realistic, and then optimistic we go 2 orders of magnitude above, and conservative we go 2 orders of magnitude below. But it's based on 2 references from the quantum optics community, where they demonstrate that they can achieve that level of noise in a fiber.
Okay, thanks, Joachim. So that answers the questions of Axel.
Okay. I think I have 2 questions that are very related to lasers. So the lasers that I know, like a non-planar ring oscillator laser, has a kilohertz line width. So why did you assume a gigahertz line width of your laser? And then the second is, what did you mean when you say that that there is not a phase modulation, but there is a frequency sideband? To me, those are the same things.
So we didn't assume a gigahertz line width of the laser. This is maybe it was misleading in this figure. It's the separation between the carrier line and the first sideband.
So there's still a lot of laser power at.
Yeah. Mm-hmm. Yes. Oh, sorry. What was your second question? It was about the optical rectifier.
It's
Like
just sort of why is there no phase modulation, but there is a sideband? I think that was a statement, like in a previous slide, that you said there is no phase modulation, but there is a sideband.
Yeah. So in this effect, yes. So that means, if you integrate for more than one gravitational wave period, you average out the phase modulation. If you can probe in between, then you would find something. But if we look at high-frequency gravitational waves, this is then, yeah.
Okay, so I would say we have just 2 more hands up, one there and then Diego, and then we stop for now and continue later. So.
Yeah, hi, thanks for the great talk. When you're not in the long wavelengths approximation anymore, what do you do? Do you switch to the TT frame, or how do you do the calculation? You have this like kink in your sensitivity curve. I assume that's where it happens, right? So what do you do at higher frequencies?
Yeah, so there are different terms contributing to the limit, which depend on the integration time and the exact frequency. So,
but what frame do you use?
Your
point is, you cannot use the proper detector frame anymore at these high frequencies.
Yes.
I mean, I agree, but I mean, I'm just like curious how you do it.
But in the TT frame.
Maybe either Valerio or Joachim. No.
I think in principle you can use any frame at any frequency range because it's GR, so it has to be frame independent. It's just that one frame is more convenient than the other. And the statement is that at high frequencies you cannot build a rigid detector. But rigid detector does not mean that you have to use the proper detector frame, and non-rigid detector does not mean that you have to use the TT frame. Elina showed this calculation where we used the quote wrong or the less advantageous frame, and it was very painful. But yeah, if you accept that pain, then you can do it in any frame.
Yeah, so for the free-falling detectors, we explicitly compared both frames, and then for the rigid ruler, we discussed it here.
Just Valerie, because you organized it, that's why you're allowed to speak. So.
Oh, and that's a cool privilege, because I don't think your question has been fully answered. So what we assume for this plot, we assume that the masses are free-falling, right? And we assume that over the entire frequency range. And so what happens at that kink is simply that we go to the regime where you start oscillating of integration over the oscillation of the gravitational wave, right? So that's where it's the kink. It's the same kink that you would see in an interferometer at that scale. So we're not changing dynamically. You should, if you actually had a setup which you thought was a rigid ruler, right? You should not just make that assumption flat over the entire range. Here we're assuming it's free falling, and we're keeping that assumption all the time.
So many thanks. So the last question for this very short round was supposed to be goes to Diego, and then we convene after the second talk. So
yeah, well, maybe also is something that we can discuss later.
Okay,
but
then
then we discuss it later.
So I will ask it and we'll discuss it later. So I wonder if you have thought about a network of atomic clocks, because you can also you can also switch to the same frequency and maybe reduce the main guy and look for the sideband in interference.
Yeah, at least
we can leave it for later.
Yeah,
if you
at least
want.
we considered having, like for the optical rectifier, to have 2 copies of them. Ideally would be more, but 2 such that they can capture a different phase shift. But yeah, more should be explored.
Okay, then let's thanks Elina again.